I want to share with you some absolutely amazing geometric gems that really go back to antiquity, that really are based on just cones. And not surprisingly, they're called conic sections. Because what we're going to do is we're just going to take a cone like this, and we're going to slice and dice it in all sorts of different ways to reveal all sorts of hidden geometric structure, which will lead to wonderful, wonderful geometric objects. So first, let's take a cone. Now, technically, by the way, we should always be thinking that the cones are kind of a double-coned cone, kind of like this. You see how there's kind of like a cone and then a cone upside down like that. So really, that's what we're thinking about. But just for the moment, let's just think about a single cone. So imagine an upside-down ice cream cone, if you will, or you could do it this way and then be more. Okay, so here's the first question. What if we were to cut this cone in a way that actually is parallel to the base? What would we get? Well, you could almost make a guess if you want. Let's try it right now live. So I'm going to come down to the chopping cam here. And if you bring it down, and I now have to cut it, you see parallel to the base. And here I go. Oh my. No one said math is easy. But when you do it, what do you get? You get something that's actually the boundary of a circle. You get a perfect circle. And so when you cut a cone, parallel to the floor, you get a perfect circle. Now that's one I just did for you live. I can actually show one. Let me actually now show you one that has been done in advance. You're going to love this one. This is really cool, by the way. Maybe as cool as mine. Check it out. So here's the cone, and when you cut it, look at that. Perfect circle. Great. So there's the first one. The first conic section is a circle. So a circle is an example of a conic section. But you're saying, hey, I want other conic sections. And I'm saying, you know what? I understand. So why don't we take another cone, and the question now is, what happens if we were to cut it askew, not parallel to the floor like before, but just a little bit kind of askew some way? What would we get? Well, can you imagine what we could get? I think you can almost visualize that. It seems like we'd get something that's kind of like a circular thing, but it would be kind of oval. Well, let's see if that actually happens. Let's go right now live to the chopping board cam. Here we go. And now instead of cutting it parallel like this, I'm going to cut a little askew. Cut a little askew like this. Let's see what happens. You ready? Here we go. Askew cut. Ooh. Wow, that was askew. Excuse me, please. But what do I get? Check out what you get. You do get an oval type shaped thing. And in fact, this oval is an example of what's called an ellipse. It's a very special type of oval that you get by cutting the cone askew like that. So an ellipse is in some sense a kind of generalization of the circle. So now let me show you a really, really beautiful one that you're going to just think is amazing. This is one that I did not do, but I could have done. So let's go back to the cam. And now what happens if I cut askew like that? You see a beautiful oval, and that oval is an example of what's called an ellipse. And so that's an example of an ellipse. Really, really neat. So that's kind of fun, isn't that? Okay, so that's an ellipse. It's a generalization of the circle, if you will. And now, let's try another one. What I want to do now is I want to take the cone, and I want to cut it now really askew, but now I want to be parallel to an edge. So here's an edge right here, and I want to cut parallel to that edge. What would I get? Well, you can see now it's no longer going to kind of cut it like this where it cuts across. It's going to kind of cut it down like that. Let's see what we get. So let's go live to the cutting board cam. And now I'm going to try to cut parallel to this. Not easy to do, but I'm doing it right now live. Let's see what happens. Do we see what happens? The sound effect really does help me. Now, so I tried to cut it as best as I can, parallel to this. It might not look very parallel, but let's look at what I get, the answer. Look at that. That is something you've seen and loved before. That is an example of a parabola. There's a sad face parabola right there, and there's a happy face parabola right there. Isn't that beautiful? That is an absolute beautiful thing. And so a parabola is another example of a conic section. Conic section. Now I'll show you a really beautiful one. If you want to see a real pretty one, here's a real pretty one. Check it out. Now, what I'm going to do is I'm going to cut parallel to this side right here. And check out that that cut is really, where are you? You see how it's parallel? And what do I get? I get a beautiful sad face or happy face parabola. Isn't that neat? So a parabola is an example of a conic section. And the last one I want to look at really is the one that involves that double upside down, right side up ice cream cone. And now I want you to imagine what would happen if I were to cut it right perpendicular to the floor or parallel to, imagine that kind of center core axis. Well, you see now, the other ones, there were only one piece. Like if I did parallel to this side, it would never hit that side. If I did straight across, it would never hit this side. But if I'm going to do now actually parallel to the core, you see it's actually going to hit the top wing and the bottom wing. We're going to have two wings. We're going to have two wings. And I'm not going to really try to cut it right now because it's going to be too complicated and this will go off. But I'm going to have two wings, a wing right here and then a wing right down here. And what would it look like? Let's just go to the close-up cam and see what one of the wings would look like. I'd have this. And now when I actually cut it, see how I cut it parallel to the straight up and down, and what I get is something that kind of looks like a parabola, but it's not. It's a little sharper, a little more elongated, and this is an example of a hyperbola. So this is hyperbola, and there's one on the top, and then there's one on the bottom. So there's two of them, you see? One from the top wing. If you come back out to the big camera, you'd see it here, that one is on the top part up here, and then one also we got to cut down here on the bottom part too. So a hyperbola has two parts, and those are examples of the conic sections. And we're done with the cooking segment part of this. So I'm going to watch how I can make a Ginsu knife disappear. Watch this. Woo! Thank you very much. And now I'm going to make the cutting board disappear. Ready? Ooh! Thank you very much. Okay. Now, that really gives you a visualization of what these things are. But now I want to show you kind of geometrically what they look like. And you can actually describe these things by rules. So for example, a circle. Well, you all know what a circle looks like. Yeah. But let me now tell you how to think about the circle in kind of a more conic-y section way. It's actually the collection of all points that are equidistant from a fixed point. Now that's a very fancy way of saying something, and we have to figure out what it's saying. So it's a very fancy way of saying that I have a fixed point. In this case, it's going to be this origin point right here. And I want all the points that are the same distance away from that fixed point. So now you see that's going to be all the points that kind of satisfy the fact that their distance away is this distance right here. Well, you can see what I'm sweeping out. I'll try to do it live. It's not so easy, by the way, but I'm going to try to do it live just for you. So these are all the points that are that given distance away. And look what I'm getting. You know it. You love it. You've seen it on CDs and DVDs all your life. It's the perfect circle. It's the perfect circle. And so that's the official geometric definition of a circle. It's the collection of all points that are equidistant from a fixed point here. So that's that. Now I can generalize that a little bit, and we can actually produce the ellipse. The ellipse is a slight generalization where what we do is we take two fixed points and we look for the collection of all points that are such that their distances, the sum of the distances from these 2 points is always constant. So let me just say that again. So for example here, take the distance from this point to that point and the distance from this point to that point and make sure that the sum of those two lengths is always the same. Which if you think about it means just I go around this way now, and that would have the property that all those distances will have the same sum of distance length. And if I do that, you can actually try this with a pin and some string. And I'll try doing that right now live. Here we go. Oh, shoot. Ooh, not good, not good. Okay. Oh, I'm doing it. I'm doing it. I'm going live. We're going live. Ooh! If your string shrinks down, oh. Now look at that. That actually is an example of an ellipse. It's a very special type of oval. Not every oval is an ellipse, but every ellipse is an oval, and it's given by these 2 points which are called the foci. Each one is called a focus. And a more beautiful picture of such a thing is right here. So here you can see an actual attractive version of one that's longer and narrower, you can see, but that's how you build them. Now you can actually build the other conic sections in kind of a similar way, but they're a little bit more complicated. So let me actually show you one. Give me a particular point. Boom. Give me a particular line. Boom. And now let's take a look at all the points that have the property that their distance from the point is equal to the distance from the line. Now this is weird. This is weird. Because what are all the points such that the distance from the point and distance to the line is the same? For example, here I pick this point right here, because this distance and that distance are the same. But what about as I move this way? Well, to find the distance to the line, you're always looking for a perpendicular distance. And so what I have to do here is I have to figure out a point. If I come out here, I've got to arrange this so that that length is equal to this perpendicular length here, which would kind of be like around here maybe. And then over here, I'd pick a point that would be kind of over here. And then a point over here would be kind of this length, because you see this length here, it's supposed to equal this length right here. And when you put these together, you sweep out actually a parabola. That's a geometric definition of the parabola. It's all the points that are equidistant from a fixed point and a line. In this case, the fixed point would be about here, and the line would be here. And check it out. If I look at this point right here, that length and this perpendicular length should be the same. And this length compared to that length should be the same. That's the definition. That sweeps out what we call a parabola. And then finally, the last one is, what if I do an even more complicated thing? Given 2 points, so I take 2 points, let's say one right here and one right here. These are called the foci. Let's take a look at all the points such that the absolute value of the difference in distances between these 2 points are the same. Well, hard to imagine what that would look like, but it turns out it's exactly the hyperbola. And let me just show you that really fast with a kind of quick little example. The idea is if one focus is here and one focus is here, then if I pick this point right here and take a look at this distance and this distance, and I take a look at the absolute value of the difference between this length and that length, which is kind of like this length right here, that should be the same if I picked any other point. So let me pick a point right here and look at this distance and this distance. Then if I take this length and subtract that length, that kind of gives me this little length right here. And notice that that length is the same as taking this length and subtracting that length. And so this length and that length are the same. Hard to kind of see, isn't it? It's a little more complicated because it's differences, absolute values, differences. But that is a geometric way of producing the hyperbola. So the bottom line is, conic sections come from taking a cone and slicing and dicing in various ways. Slice parallel to the floor, you get a perfect circle. Slice slightly askew, you get a perfect ellipse. Slice parallel to one of the edges, you get a parabola. And slice perpendicularly to the floor, you get 2 wings, a top and a bottom, and they form the perfect hyperbola. And you can produce those things in the plane by looking at various rules and looking at all points that satisfy some things with respect to some foci. or some other things. Anyway, the important thing is that you now appreciate the beautiful geometric objects known as the circle, ellipse, parabola, and hyperbola. I'll see you soon.